Hello everyone, today I'm sharing with you my CS50P final project, the electrophilic warhead matter for covalent compounds. This project is inspired by covalent drug discovery. I'm interested in finding covalent drugs that are approved or in clinical trials because these real-world examples offer valuable insights for designing new covalent drugs. To explore this, I developed a program that helps identify covalent compounds based on their electrophilic warhead. I started this project by breaking the program into smaller tasks. This program should be able to do at least two things. First, the program needs to take in a collection of compounds. For this project, this input can either be the library of compounds in clinical trials or approved drugs. Second, it needs to identify which of these compounds look like covalent drugs by checking whether their structures contain a reactive electrophilic functional group. I wanted this program to create a list for each electrophile type, categorize any potential covalent compounds, and draw the compounds with their electrophilic warheads highlighted. In this presentation, I will introduce covalent drugs, including how they bind and how SMILES or SMARTS notation is used to represent compounds and electrophile warheads. Electrophilic warheads are the functional group that form covalent bonds with target proteins, and they are a defining feature of covalent drugs. I will also walk through three pattern recognition strategies I explored while developing this program. I will finish by demonstrating how this program identifies potential covalent compounds from a list of clinical trial candidates and classify them based on their warheads. Covalent drugs represent a relatively small but important subset of approved therapeutics. Most drugs on the market are non-covalent. These drugs bind reversibly to their target proteins using interactions like hydrogen bond or hydrophobic forces. These interactions are transient, allowing the drug to bind and unbind repeatedly. In contrast, covalent drugs are designed to form a covalent bond to their target protein, typically through a reactive electrophilic group called a warhead. This bond is often irreversible. Covalent drugs have gained increasing attention in recent years because they offer several potential advantages, including enhanced potency and prolonged target engagement, which can translate into more durable therapeutic effects. As examples of non-covalent versus covalent drugs, on the right we have two EGFR inhibitors, gefitinib and afatinib. Both are approved treatments for non-small cell lung cancer. They bind to the same pocket on the same target protein EGFR, and they share an identical core structure designed to fit into the ATP cleft to block EGFR's activity. The key difference lies in how they bind. Gefitinib interacts reversibly through non-covalent interactions, while afatinib forms a covalent bond with EGFR through its acrylamide-based warhead. In the covalent drug world, a warhead is usually an electrophile that forms a covalent bond with a target protein. In the previous slide, the EGFR inhibitor afatinib has an acrylamide-based warhead. Here we have another example, the COVID-19 treatment nirmatrelvir or Paxlovid. Nirmatrelvir works by binding to the virus's Mpro protein via a nitrile group. In other words, the nitrile group is the warhead of nirmatrelvir. Nitrile and acrylamide are two examples of covalent warhead, and there are many other warheads under development by the drug discovery community. On the bottom left is the SMILES notation of nirmatrelvir. SMILES is a common way to represent a compound, and it looks like an encrypted string. The nitrile group is represented as C-N. On the right is the crystal structure of nirmatrelvir bind to the cysteine 145 of the virus's Mpro protein. there is a covalent bond formed between the drug's warhead and the thiol group of cysteine 145 of M-Pro protein. The goal of this program is to go through the list of drugs that are already approved or currently in clinical trials and find compounds that has a functional group that looks like a warhead. I decided to focus on 4 common warheads. They are nitrile, acrylamide, beta-lactam, and boronic acid. In this program, the warheads are defined using its SMART notation, which is similar to the SMILES notation we saw in the previous slide. When I first started designing this program, I knew I wanted to define each warhead type as its own list, and then add identified compounds to the corresponding list. Around that time, the CS50P course introduced object-oriented programming, and I realized I could redesign the program to take advantage of this feature in Python. Object-oriented programming, or OOP, allows developers to create objects based on a blueprint called a class. This makes it easy to reuse shared functions and structures across many objects. In the first version of this program, I had a lot of redundant code because I manually created a separate list for each warhead type. After learning OOP, I rewrote the program so that each warhead is represented as an object, meaning each warhead list is now an instance of the moiety class. One clear advantage of using OOP is versatility. For example, if we want to analyze an in-house compound library that uses more than the 4 default warheads shown here, all we need to do is add the new warheads to the moiety class. With that, all functions automatically become available to the new warhead. In other words, this program is expandable and can be used to analyze specialized compound libraries. In the next section, I would like to introduce the 3 strategies I tested for detecting warheads in compounds. This task is more difficult than I originally imagined, but finding a solution was an interesting learning process. I rewrote the program multiple times along the way as I shifted toward a better method. Because the compound can be described using a SMILES notation, the first strategy I tried is to use the simple Python string find function. Taking the Amatrovir or Paxlovid as an example, it is easy to find the nitrile group in the SMILES representation of Paxlovid. However, when it comes to finding the acrylamide group in the cancer drug sotorasib or Lumakras, a simple Python find function does not help us with identifying the acrylamide group in the Lumakras' SMILES. This is simply due to the arrangement of the SMILES notation of this compound. When sotorasib is represented in the SMILES notation, the acrylamide group is not a continuous string. Rather, it is kind of split in the SMILES notation. From this, I realized that I need to incorporate some kind of functional group-based algorithm. I did some literature search and found the IFG algorithm published by a former Novartis scientist, Peter Ertl. This algorithm provides an elegant way to finding functional groups and is very popular among Cheminformatics scientists. The IFG algorithm is designed to crawl through atoms of a compound and use a series of steps to identify functional groups. I changed to using IFG in the 3rd version of this program, and the algorithm successfully identifies acrylamide group in sotorasib and in many other acrylamide-based covalent compounds. I was very satisfied when I solved this problem, but this isn't the end of the story. I found another problem when I attempted to identify the beta-lactam group in another covalent drug, penicillin. Turns out, because IFG's algorithm defines functional groups by crawling through and labeling atoms in a non-traditional way to accommodate not only the arrangement of atoms, but also the environmental influence on atoms, the beta-lactam group of penicillin is not considered a functional group. by IFG's definition. As a result, my search for the solution for this program continues. After some more search, I settled on another popular Cheminformatics tool, RDkit, developed by Greg Landrum. RDkit has a function called substructure match, and it is the perfect solution for finding functional groups from compounds. I tested the substructure match function for many known covalent compounds, and it does a great job at picking the warheads. From this, I decided to use RDkit in the 4th version of this program. During the development of this program, I found RDkit to be a very useful tool for working with chemical structures. In another project, I used RDkit to cluster compounds based on structural similarities, which is a very useful way to analyze compound libraries. RDkit is also great for drawing compound structures, and later in the demo, you will see this program output results as a list of drawn compounds. So after a long search, I finally found a strategy that works for detecting warhead-like functional group in molecules. With this approach, the program can now process a list of compounds, detect the warheads, and classify compounds into appropriate groups. The next step is to retrieve input data. We can download the list of drugs that are approved or in clinical trials directly from PubChem. PubChem provides this information in the format of JavaScript Object Notation, or JSON. So JSON becomes one of the input types this program can read. I also want the program to work with in-house compound libraries. To do that, this program also takes a simple list of compounds, as long as each compound includes its SMILES notation. Before the demonstration, I'd like to give a brief overview of the program. This program is organized into 3 main sections. The first section is the moiety class. I'll show how the class uses OOP to define each warhead type as its own instance. I'll also highlight the class attributes and the 2 main functions, one that matches SMART pattern, and another one extracts and generates compound IDs, SMILES strings, and compound names from a JSON file. Next, in the main function section, I'm going to demonstrate 4 things the program can do. First, I'll show how this program prints all supported warhead types. Second, I'll show how this program instantiates a boronic acid compound list and find compounds that contain a boronic acid group. Similarly, as the third task, I will demonstrate how this program finds compounds that contain a nitrile group from a customized compound list. And finally, I will loop through all available warhead types, categorize compounds in clinical trials by their warhead type, print their compound IDs, visualize them, and output their structure as a PNG file. The last section of this program are a few utility functions, which I'll touch on very briefly at the end since they're mostly supportive. Okay, let's start looking at the actual code. The first section of this program is the moiety class. This class inherits from Python's list class, so every created instance of the moiety class is actually a list of compounds. I designed this program to create and identify compound lists for every warhead. I use init function to define an attribute for the moiety class, which is pat or pattern. I wrote a class method that returns all available warheads. Later in demo, you will see one of the tasks is to instantiate all available warheads by calling the class method. The pat_smart function defines the smarts for each warhead, and what it does is it returns the smarts notation for the warheads that will be instantiated. Additionally, we have a getter and a setter. These are here to protect the access to the class's attributes. The getCompound function is one of the main functions of this program. What it does is it takes a JSON file as input, and then it matches the warhead smarts to each of the compounds in the JSON file. If the warhead SMART is found in the compound, then that compound gets to be appended to the list. And by the end of the loop, what we get is a list of compounds that has the designated warhead. The getCompound function actually talks to another function called CID smells name. The CID smells name function is outside of the class because it does not need the access to the class's attribute, which is the SMART notation or pattern. Let's go to the CID smells name function. What the CID smells name function does is it takes the JSON file and it yields one at a time the CID of the compound along with the smells and the compound name. We have to use yield here instead of a return because usually the JSON files we handle are really big files. For example, the JSON input for the compounds in clinical trials has over 14,000 entries. This file is 81.3 megabytes. If we were to use return instead of yield, it will take a lot of memory space. In Python, a function uses yield, like this one, is called a generator. Going back to the class, similar to the getCompound function, we have the fromSmilesList function. What it does is very similar to the getCompound function. It takes a list of smiles, usually from a customized compound library, and from the list, it matches each of the compounds to the SMART of the warhead. If the compound has the warhead, then that compound gets appended to the list that will be returned. I will skip the drawMatches function because it's a utility function that visualizes compounds. We will see the PNG output of this program in the demo shortly. To demonstrate what this program does, I will be showing you 4 things this program can do from executing commands in the main function block. The first task is printing all supported warheads. We will do this by calling the class method. Let's run this. Here you can see all supported warheads are printed. The second task is to demonstrate how this program finds possible covalent compounds from a JSON file. What will happen in a second is the program will instantiate a list called boronic acid and run the getCompound function. The getCompound function takes a JSON file that contains compounds that are in clinical trials and identifies compound that has a boronic acid group by matching SMART's notation. If the compound has a boronic acid group, it will be appended to the list. This program will print the CID and the name of identified compounds. It will also draw these compounds with the boronic acid group highlighted and save as a PNG. Let's run this section. Here you will see the program prints the SMARTs of boronic acid. This is to remind us which warhead we're looking at. It will print the IDs and the names of identified compounds. If we go over to the PNG output, we will see identified compounds being drawn with the boronic acid group highlighted. In the next task, we will do something very similar. The only difference is this time we take a compound list that is not a JSON file. I do this to mimic the situation where we have a customized compound library. From the compound list, we will extract compounds that has a nitrile group. We will instantiate a list called nitriles, and the program will check each compound in the list to see if the compound has a nitrile group by matching the SMARTs. Compounds that has a nitrile group will be printed and drawn. Let's run this. Here we will see that the program finds 2 compounds that has a nitrile group. I do have a very simple list, and there are only 2 compounds that has a nitrile group here. Similar to the previous task, there is a PNG output. Here you will see 2 compounds being drawn here. Now I will show you how this program identifies and categorizes compounds in clinical trials. To do this, first I leverage the class function to instantiate 4 empty compound lists, 1 for each warhead type. Then the getCompound function talks to the CID smiles name function, which is a hidden action in this code block here. Then the CID smiles name function takes the JSON input, and the function's generator yields the compound smiles, CID, and name one by one. The generated smiles will be checked by the getCompound function, and the getCompound function will figure out if the compound's smiles contains a match to a warhead's smarts. If it does, the compound will be appended to the corresponding warhead list. The identified compounds will be printed on the screen. The compounds will also be drawn and saved as a PNG file. Let's run this. As the output, we'll first be notified about the warhead type, a quick summary of all the compounds identified to have a nitrile, and the number of items in the nitrile list. We'll see the program prints compounds that have a nitrile group, its CID, and its compound name one by one. To go through the entire JSON file of the compounds in clinical trials, the process takes 20 minutes. Once the program finishes identifying compounds with a nitrile, it'll move on to acrylamide, and then beta-lactam, and then finally boronic acid. While this function continues to finish everything, I will go back to the presentation. To summarize the results of this project, I have analyzed compounds in clinical trials and compounds from the Orange Book, which contains all FDA-approved drugs. On the day I downloaded the input data, there are just over 14,000 compounds in clinical trials. The number of identified covalent compounds in each category is summarized here. Likewise, I listed the number of identified compounds from the 3,256 FDA-approved drugs. I wanted to add that there is in fact a caveat of the approach I took for this program. We should know that not all compounds identified by this program are covalent compounds because sometimes functional groups are added for other purposes. For example, we know sometimes we add a nitrile to a compound to increase solubility. I think the results produced by this program will have to be verified and make sure all identified compounds are indeed covalent. Nevertheless, I think the compounds identified here are good starting points for analyzing compound libraries. Here are the references for this work. With that, I think it's time to go back to the program and check the outputs. Coming back to our program, it has finished nitriles and is still working through the acrylamide list. The program will move on to look for compounds that has beta-lactams in a second. We can check the PNG output for acrylamides. Here you can see all compounds identified as containing an acrylamide warhead. You'll probably recognize a famous one right away, ibrutinib. The structures could definitely look cleaner, and that's something we can improve in the next version. The nitrile visualization definitely looks much cleaner. And we also see very familiar ones like adagrasib over here. And nirmatrelvir over here. And also another one is a KRAS G12C inhibitor, MRTX1719. These are known compounds that have a nitrile group. So while it's continue to finish everything, I don't think we need to sit here and wait for it to finish. Of course, instead of generating an image, we could have the program write everything into a CSV to make downstream analysis easier. While we're talking, looks like it has generated an output for beta-lactams. And we'll see right away penicillin, ampicillin, amoxicillin. These are non-beta-lactam based antibiotics being identified here. So I will let it continue running in the background, but I don't think we need to sit here and wait to finish everything. With that, this brings us to the end of this presentation. Thanks for listening.